For most people, opening your eyes will expose you to something bright. That brightness is made possible by light, typically in this case, visible light. But what is light? Based on the Encyclopedia of Britannica, light is an electromagnetic radiation that can be detected by the human eye. Wait a second. Radiation? That's particles, right? But isn't light a wave? Well, the thing is, it's both. But how? All of this can be explained by the quantum theory of light. But before that, let's get to know about something called the electron. In 1987, J.J. Thomson conducted an experiment that studies the properties of a cathode ray. During his experiment, he detected particles that were moving from the negatively charged electrode, or cathode, to the positive one, or anode. He measured the charge per mass of the particle and discovered that it is 2,000 times lighter than hydrogen. The particle is an electron. He won a Nobel Prize in 1906 because of it. Well, but what does that have to do with anything? Well, it helps us to know more and understand more about black body. You see, black body is an object that absorbs all electromagnetic radiation that falls upon it, without reflecting or transmitting any of it. The spectrum of light emitted by that heated object is called black body radiation. The spectral intensity of black body radiation peaks at a frequency that increases the temperature of the emitting body. In the late 1890s, scientists struggled to sync the results of careful observations with classical electromagnetic and thermodynamic theories. That is, until Max Planck. In an attempt to explain the nature of black body radiation, Planck postulates that light energy does not flow continuously, but come in discrete packets called quanta. He proposed that heat energy, E, is proportional to the frequency and to Planck constant, which is 6.626 times 10 to the power of the negative 34. This understanding gave him the ability to understand the photoelectron effect, which by definition is a phenomenon where electrons are released from a material that emits electromagnetic radiation. However, scientists could not fathom why high intensity yet low frequency light could not cause it to emit electrons, yet low intensity but high frequency light can. Well, Planck's hypothesis led Einstein to believe that electromagnetic waves could behave like a particle. He noticed that in order for an oscillating atom to lose its energy, they have to jump from a higher energy orbital to a lower energy one. The energy loss is then the one that is represented as an electromagnetic wave. Because the energy levels of the oscillating atoms are separated by HF, the energy carried off by the electromagnetic wave must be HF. Similar to Planck's theory, Einstein proposed that light comes in discrete packets called photons. Photons have no mass, but does have momentum and energy. It can be defined as E equals HF. Its momentum is measured by Planck's constant divided by the wavelength, which will be explained further. When photons interact with electrons, they release a certain amount of energy. Certain energy, or in this case, is considered as work function, is needed to eject electron from a metal surface. The amount differs among the types of metal. If a photon has an energy just as big as the work function of that metal, the photon could transfer that energy to the electron, causing it to release itself from the metal surface. In conclusion, the effects does not lie on the intensity of the light, but rather the energy of that photon, which is proportional to the frequency of that light.
In the early 1920s, when the particle-photon nature of light suggested by the photoelectric effect was still being debated, The Compton experiment gave clear and independent evidence of particle-like behavior. Arthur H. Compton explained and modeled the data by assuming a particle-photon network for light and applying conservation of energy and conservation of momentum to the collision between the photon and the electron. The scattered photon has lower energy and therefore a longer wavelength. According to the Planck relationship, he observed the scattering of X-rays from electrons in a carbon target and found scattered X-rays with a longer wavelength than those incident upon the target. The shift of the wavelength increased with the scattering angle according to the Compton formula. The formula consists of properties including incident photons and scattered photons, in which they are related to the momentum conserved. The effect was first demonstrated in 1923 by Compton and was awarded the Nobel Prize in 1927 for the discovery of the effect named after him. Compton's graduate student Y.H. Wu later verified the effect. Wave-particle duality, the principle of complementarity and wave nature of matter. The evidences for the description of light as waves was well established at the turn of the century when the photoelectric effect introduced firm evidence of a particle nature. A wave-particle dual nature has the characteristic of electrons as well. In 1928, by the Danish physicist Niels Bohr, a complementary principle basically states that a complete knowledge of phenomena on an atomic dimension requires a description of both wave and particle properties. Depending on the experimental agreement, the behavior of such phenomena as light and electron is sometimes wave-like and sometimes particle-like. It is impossible to observe both the wave and particle aspects simultaneously. Together, however, they present a fuller description than either of the two taken alone. Wave nature of matter. Davison-Germer experiment demonstrated the wave nature of the electron, confirming the earlier hypothesis of de Broglie, which will be explained further. But basically, in 1923, a French physicist graduate student named Prince Louis Victor de Broglie made a radical proposal based on the hope that nature is symmetric. If the electromagnetic radiation has both particle and wave properties, then nature would be symmetric if matter also had both particle and wave properties. The Bohr's model. Bohr proposed a solar system-like model of the atom, where a nucleus contains the atomic number of positive charge surrounded by an equal number of electrons in orbital shells. The electrons orbiting were consistent with Planck's quantum theory of radiation. These orbits were associated with definite energies, meaning that the energy of an electron inside an atom is not continuous, but quantized. These levels are thus labeled with the quantum number 1 2 3 A to Z. Electrons can only move from one orbital to another allowed orbital at one time. If an electron drops down from N2 to N1, energy is emitted, and if the electron moves up from N1 to N2, energy is absorbed. The amount of energy that is either absorbed or emitted is called quanta. This way, he claimed, could be determined using the Rydberg formula to explain how the electrons emit light as they move from one orbital to another. De Broglie hypothesis. In 1923, the De Broglie states that particles of matter also had wavelengths and could behave as wave, but just as a photon did. In 1925, two American physicists performed the Broglie-based experiment that showed interference patterns with electrons. This behavior showed that whatever quantum law governed photons also governed particles. The wavelength of particles such as the electron is very small compared to the photon. For larger objects, the wavelength is even smaller still, quickly becoming so small as to become unnoticeable. He arranged the terms of Planck-Einstein relation to apply to all types of matter. He came up with an equation used to describe the wave properties of matter, especially the wave nature of the electron, as mentioned previously. Lambda equals to h over p, where lambda is wavelength, h is Planck's constant, and p is the momentum, which is mass times velocity. What is light really? Is it a wave or a shower of photons? There seems no likelihood for forming a consistent description of the phenomena of light by a choice of only one of the two languages. It seems as though we must use sometimes the one theory and sometimes the other, while at times we may use either. We are faced with a new kind of difficulty. We have two contradictory pictures of reality. Separately, neither of them fully explains the phenomena of light, but together they do.